The publish-subscribe or pub-sub communication model of MQTT offers a lot of benefits over the traditional pull and response model, but it's not immediately clear how the system works or what role the central server, called the broker, actually plays or what it is capable of. In this video, we'll take a closer look at the broker, see how it fits into the pub-sub architecture, and see what advantages it can provide for industrial automation applications. The main benefits of having a broker are that it eliminates vulnerable, insecure client connections, can easily scale from a single device to thousands, and manages and tracks all client connection states, including security, credentials, and certificates, and it does all of this without compromising security or putting strain on even the most tenuous networks, such as a cellular or satellite network. The first question you may have is just what is a broker? And the answer is that it is simply software running on a computer. It could be any computer, from a Raspberry Pi to a PC to a server. It could be on-premise or in the cloud, and it could be self-built or hosted by a third party. Broker software is available as either open source or proprietary with extra features added on. The second thing to understand about the broker is that it acts somewhat like a post office, where instead of a device sending messages to and getting them from another device directly, peer-to-peer, they're sent to the post office, the broker, and then it is forwarded to everyone that needs that message. The big difference is that MQTT doesn't use the address of the intended recipient, it uses a subject line called the topic, and anyone that wants a copy of that message just subscribes to that topic. So, the flow of data is, the transmitting client publishes a message under some topic to the broker, and then the broker sends out that message to everyone subscribed to that topic. In this model, there is no direct connection between each client, just one outbound connection from the client to the broker, and that's it. Since everyone is connected to the broker, they're interconnected via the broker. It can relay messages between all the connected clients. Unlike most communication protocols, this message relay is not restricted to a one-to-one model. Since a message isn't targeted to a single device and instead uses a topic for unique identification, it's possible to have many devices subscribe to the same topic. Then, a data producer just needs to send out one message, and the broker will send out many messages, one to each subscriber. This one-to-many capability means that you can get all the data you need to all the devices you need, even thousands of other devices using just that one connection from the original client. Similarly, you could have many devices publishing over the same topic, but have only one subscriber to that topic, creating a many-to-one model for something like a database that logs all messages. The broker handles all of these scenarios easily by using topics to manage the messages. Each client can both produce and consume data by both publishing and subscribing. A big advantage of having this two-way communication means that devices can publish sensor data while still being able to receive configuration information or control commands. In other words, MQTT is a bidirectional communication protocol. This makes it powerful for both sharing data as well as managing and controlling devices. The broker is the central key to this powerful solution. Now let's take a look at a typical SCADA system today, where devices and systems are tightly coupled to each other and require a lot of connections, open ports, and probably a lot of IT assistance and maintenance. This architecture has some serious security implications, with many open ports at each device. Every device has to manage each connection to all the other applications and devices, and a major change to even one element means having to go into many other devices to keep the system running. This requires a lot of man-hours for small updates, and that's before accounting for troubleshooting and ongoing maintenance. A lot of the time, the devices are simply not built with the necessary network resources to manage all of these connections and provide them in a secure manner. By moving to an MQTT architecture with its central broker, we see how devices and applications become decoupled and more secure. Now, the broker becomes the central location for security because all clients have to authenticate against it. Only one port is required to be open to the broker, the secure port 8883, and all other locations have their firewalls intact. No more pinholes with port forward rules, security by obscurity, or leaving clients open to attack. MQTT does all of this using transport layer security or TLS encryption, with username and password protected connections, and optional certification that requires clients to provide a signed certificate file that matches that of the server. On top of all these levels of security, having just the broker aware of each client and using topics to communicate means that each client is unaware of the IP addresses and domains that the other clients operate on. If you are concerned about having a single source of failure, most broker software and clients have an automatic handover to a redundant or backup broker should the primary go down. They can also often be set up to share the load of clients across multiple servers on-site, in the cloud, or a combination of both, with the ability to shift the load of clients as servers get overwhelmed or even go offline. All of this makes the entire model very scalable and flexible to change and growth. Furthermore, brokers are flexible in that they can support both standard MQTT messages and topics, as well as MQTT compliance specifications, such as the Sparkplug specification, and they can do it all with the same server, at the same time, with the same levels of security. To find out more about Sparkplug, check out our other videos. All MQTT implementations have their clients publish data only when there has been a change in value. But it's important that new clients who join after some data has already been published are able to be filled in on the last known value. To handle this, another function of the broker is to store data in the form of retained messages, so that new subscribers to a topic can get the last value straight away. An example of this is a low power sensor that might only wake up and send its data every 6 hours to maximize its battery life. But if another client subscribes to that topic, you really don't want to wait that long to get a reading, so the broker will retain and send out the last value received as soon as the subscription is made. This is not long-term storage, however. The broker will not keep a historical log of messages that go through it. You would need to subscribe with a database client or something like that instead. Rather, retained messages are just a copy of the single most recent message received for some specific topic. To keep track of which clients are subscribed to what topics, whether they have received a retained topic, and to efficiently manage all of the different user accounts, the broker keeps track of all current sessions and can even store session information long-term as devices go on and offline. These are called persistent sessions and further make MQTT a strong connection model in potentially unstable network settings. For example, if a device is on a cell network and loses reception temporarily, it can easily reconnect with the broker without having to resubscribe to all of its topics, which could cost time and network traffic. Instead, the broker remembers them and they pick up right where they left off. Lastly, the broker also handles the birth, death, and last will and testament messages for the clients. These messages are sent to the broker when a client first connects, along with a keep alive timer, and they all keep the broker and other clients aware of the connection status. First, when the connection is established, the broker forwards the birth message out under a set topic to let all other subscribed clients know that there is a new device in the system. Then, the broker stores all of the messages, including the death and will messages. If the client ends its session with the broker, then that broker will forward out the death message so that other clients know the device is offline. While it is still connected, the client will check in with the broker regularly with a 2-byte heartbeat packet based on that agreed-upon keep-alive timer that the client chooses. So, if the broker doesn't hear a heartbeat for that length of time, then there must be something wrong with the connection, and the broker will send out that will, or last will and testament message, so that other clients know it has dropped unexpectedly, and they should not expect any more messages from that device until they receive another birth message. This is done server-side by the broker, since if the client drops, it's unable to send that message out for itself. By using the broker to manage the connection states of all the clients, you can keep your entire system healthy by putting subscribers in place to listen for birth, death, and will messages and react accordingly by shifting responsibilities, attempting reboots, bringing up backup devices, or even just notifying someone of the offline devices. It's possible to do many things with these messages or outright ignore them, but MQTT provides the tools you need to monitor and maintain an entire system while still keeping network traffic low due to the variable keep-alive timer and the tiny load of the heartbeat packets. So there you have it. The MQTT broker is a key part of the publish-subscribe or pub-sub system. but it is nothing more than software running on a computer at a given location. Thanks for watching.